Hi everyone, we're the Smart Spine Tape Senior Design Team. I'm Kelsey.
I'm Bethany.
And I'm Jessica. This video is our functional prototype video, and we will be discussing the engineering specifications, manufacturing, and testing of our device. The Smart Spine Tape device consists of sensors on a T-tape which is placed on the lower back and measures spinal deflection. Our customer requirements for this device were to design a lightweight, comfortable, and flexible device to measure spinal flexion, extension, and rotation. It is also important to have reliable sensors that provide an easy method of retrieving data. As a team, we then translated these customer needs into specific engineering specifications. This includes a minimum detection for flexion of 10 degrees, a minimum detection of extension of 5 degrees, a minimum detection of rotation of 10 degrees, a total sensor lifetime of 4 days, a stretchability factor of 125%, flexibility of 90 degrees, an overall size specification of 3 inches by 12 inches by 0.15 inches, and ensuring an ease of application so that the application time is less than 2 minutes. To achieve these specifications, we have two main design components: the data acquisition system and the sensor itself. The data acquisition system is composed of an Arduino Nano BLE, which is a microcontroller that uses Bluetooth to communicate data to other devices. The Arduino is connected to the silver conductive electrodes on the sensors via insulated wiring. The 4 silver conductive electrodes are connected to the ends of the 3 serpentine sensors.
Moving into the manufacturing of our device, the sensors are created by first laser cutting the strain rosette design into a plastic sheet. The strain rosette design of the sensors allows data to be taken in all directions of displacement. Then the mask sheet was adhered to the KT tape and the piezo-resistive ink was painted over the mask onto the tape as shown in this next video. The ink itself was obtained from NanoPaint, which is a materials company based in Portugal and is a proprietary pre-made ink. Some challenges we faced included shipping times and getting the ink through customs with the Toxic Substances Control Act approval. This process was done under the fume hood in accordance with the safety data sheet. After 45 minutes, the mask was then removed and the piezo-resistive sensors were then allowed to dry for 24 hours straight. The sensors were post-processed with thermal treatment in the oven at 140 degrees Fahrenheit for 20 minutes. This processing helped reduce the resistance of the sensors, which will make it easier to measure changes in resistance in the future.
Testing was performed to test our design against our engineering specifications. The first test was the tensile test, which verified that the sensors would have a consistent resistance after stretching to their maximum elongation. The tensile test showed that the tape did not sustain permanent deformation and was able to still consistently measure resistance post-testing. The next test was the flexibility test to ensure that the sensors can bend to their maximum bending angle and still function properly. Additional tests were performed to ensure the sensors changed in resistance for flexion and extension at various angles. The flexibility test showed that there was no permanent damage after bending the sensors to 90 degrees. Rotation changes were measured by twisting the tape at various angles and measuring the resistance changes. The rotation test showed us that the sensors are sensitive to rotation and able to measure a change in resistance at a low degree of rotation. The longevity of the device was measured through a 24-hour wear time test, ensuring that the tape remained secure. The sensors on the tape were analyzed to see if there was any change in resistance over the time period. The sensors were less reliable after the 24 hours and not able to get a consistent reading, but there was still some ability to measure changes in resistance. Additional tests were performed to measure the size of the tape and the time it takes for application to ensure ease of use for the users. Overall, the sensors show promising results by changing in resistance when deflected in the ways that the spine will deflect. Moving forward, we will be comparing the data obtained from our sensors to that measured in the Motion Biomechanics Lab.
Some of the future recommendations we have to utilize the Bluetooth module and Arduino to allow for real-time spinal movement tracking, develop a method of quickly alerting the user when a dangerous movement was made, enable the data acquisition and sensors to be reusable to reduce the cost of each unit of the device, and print the sensors at a consistent baseline to avoid calibrating each smart spine tape device. Thank you very much to our sponsors, Dr. Wang and Dr. Berg-Johansen. We really appreciate all of your help and support during the entire design process and have all learned a lot.